So good afternoon, everyone. My name is Maäréva Payet. I'm in charge of the Sustainable Design of Buildings and Research and Development Division at the Urbaine Réunion, which is a building design office. With me is Maxime, who is co-head of the Research and Development Division, and is also working on a PhD thesis in partnership with Urbaine Réunion and the PIMENT laboratory of the University of La Réunion. The study we wanted to present to you today relates to a coupling methodology of windows and ceiling fan occupant behavior models with building energy models. Le Réunion Design and Engineering office is part of the ILET du Centre group, which also includes a structural design office and an architecture and landscape office. We essentially focus on designing bioclimatic buildings adapted to hot and humid tropical climates. In these areas, we apply specific rules to ensure the high performances of buildings. First, effective solar protection for roof, for vertical walls and windows is essential. And this can be achieved, for example, with insulation or solar shading devices adapted to each orientation of the building. Next, the goal is to optimize natural ventilation to reduce active and energy-intensive devices like air conditioning. And we can say that in tropical climates, air conditioning represents the biggest energy consumer in the non-residential sector. When natural ventilation itself isn't enough due to extreme temperatures and humidity, we can explore alternative solutions such as coupling devices. According to Köppen classification of climates, areas in humid tropical climates classified as A include zones where the average air temperature each month is above 18 degrees and where a quantity of average rainfall reaches over several months. These tropical areas are facing many issues. According to BELDA, the surface affected by humid tropical climates, and more specifically the subclass called AW, has been growing since the period 1965-1994. And in addition, a report by James Cook University predicts a significant increase in the population in the tropics by 2050. Rodriguez also adds that 75% of the population will live in urban areas, and this means an increase in the rate of construction and the related need for energy. Given this complex context, construction practices need to be adapted, and several types of low energy buildings have been introduced. And now we come to the example of mixed mode buildings, which Brager defines as building in which different air conditioning combinations are used. We speak about passive cooling systems, which are based on architectural techniques designed to improve the differences between overpressure and underpressure on building facades. This is the real motor of natural ventilation, and it can be achieved, for example, by installing big glass louvers on opposite facades, which are windows made up of manually and adjustable slats, like in the picture. When passive systems no longer provide a comfortable environment for users, low energy systems such as ceiling fans can reduce the perceived temperature by increasing the airflow. And energy-intensive cooling systems such as air conditioning can be used only during the hottest months, but with an higher energy consumption. In these buildings, users can choose between the different devices called controls by Raja. And the controls are manipulated to restore comfort and particularly hydrothermal comfort. In this study, we focused on tropical climate controls, that is to say, windows for natural ventilation and ceiling fans and their coupled use. Users will have a significant impact on the energy consumption of this type of building by their presence in the zone, and also by the active effects of their behavior and action on the controls. And presence is essential for these actions to take place. In addition, we have noted that in tropical climates, users accept higher temperatures and humidities than in temperate climates, and the use of the different controls will be different. All the different factors make user behavior difficult to predict for design building offices. And what's in fact the role of design engineers in this context? In fact, they have to size the different devices and to estimate the building's future energy impact. A lot of design how can they do? A lot of design offices make assumptions and use conventional models, which can sometimes be imprecise for describing users and actions. And this is especially true for mixed mode buildings where different controls are available. And this can lead to oversizing system and to differences between the estimated consumption in the design phase and the consumption actually measured in operation. And this is known as the performance gap. So in this study, we looked for a way to improve the prediction in the design phase. And the methodology employed was divided in 2 steps: the modeling of window and ceiling fan behavior based on measured data, and then in second part, the incorporation of these behavior models into a building model. The work presented here is based on a case study in the humid tropical climate of the French Réunion Island, just here. And this island is exposed to southeast trade winds and thermal breezes, resulting from the difference in temperature between the surface of the land and the sea. The case study is called Îlette du Centre and is an office of almost 300 meters squared, part of a residential building. The office has 2 floors divided into several open plan areas with several desks organized side by side, just like in this photo. There is a meeting room, an IT room, and 2 individual offices. And the users can regulate temperature by generating closed airflows thanks to many manually adjustable openings that we call louvers, like this. And they can also activate ceiling fans to reduce the temperature felt on the hottest days. There is no air conditioning device except for the IT and the meeting rooms. We measured the opening of windows using magnetic position sensors. They indicate whether the louvers are open or closed. In fact, if there is contact between the sensor and the window, the value is 1, and so the louver is closed. is closed, and if the louver is open, there is no contact between the sensors and the glass, and so the sensor shows 0. Ceiling fan power and offices plug were also recording between 2020 and 2022 using specific energy submeasures. In addition, we measured air temperature and relative humidity at different places, and we used outdoor climatic data from a station situated less than 1 kilometer far from the building. Based on this data, we tried to model the behavior of windows, called louvers, and ceiling fan. To do this, we use machine learning methods. First, the occupant presence was not directly recorded. However, we have seen that the presence is necessary for any action to be taken. So we assumed that the power consumption of the plugs, including the consumption of the workstations, were reflected the presence and the level of occupancy. We therefore use the decision tree technique to estimate the number of people present depending on the power value of the plugs and the time of the day. And this is the resulting tree. Just quickly to read the rules, you simply have to go down the tree from the root node to the leaf node. Each intermediate node is the result of a test on the value of an input variable selected as a splitting parameter. Data that succeed the test is separated from data that fails the test, and branches are created. For example, the model created is able to represent the absence of people during the lunch break. For a plug power between 4 and 6.7 watts by meter square, during the lunch break, the model estimates 0 for the number of people, just here. The output of this first decision tree was used to complete the database for our case study and as input for the behavior models for windows and ceiling fan. And then different variables were used to build the behavior models. The first 2 models we tested to model the use of windows and the use of ceiling fan were modeled to estimate the use of the different controls, but independently. That is to say, opening windows alone and after ceiling fans alone. But we also try other models, and we obtain better simulation results by creating a model in which the use of window opening controls and ceiling fan use were correlated. In other words, the estimation of the level of use of ventilation ceiling fan, integrating the level of use of windows, estimating thanks first model. And for this couple model, the technique of random forest was used, and it's a classification method. At the end of the presentation, because we don't have a lot of time, we have included a reference to a full paper on the subjects, which really explain the models in detail. Okay, now we have our behavioral models for windows and ceiling fans, and after we can implement these models in building simulation. And for this, thermal simulation software allows detailed descriptions of how buildings behave over time and how they interact with their environment. In this way, engineers can estimate the future users' comfort and energy consumption, but it's essential to master the many input parameters that need to be defined. And the most common tool used in Réunion Island is the Energy Plus calculation engine. The different existing methods to incorporate occupant behavior into simulations vary in complexity. Some are more complex to implement, but can offer greater flexibility. In our study, we have adopted a method called Python plugging. And it's a new approach placed between code customization and co-simulation method. And it enables engineers to write code in Energy Plus using Python. And this method has not been widely reported, but can offer some benefits over other methods. The method we used dynamically adjusts window opening and ceiling fan use in thermal zones at each Energy Plus simulation time step. Simulation outputs here are transmitted to Python coded behavior models, which can next estimate new control levels for the next time step. And the process is integrated into Energy Plus, and so it simplifies the workflow for engineers without additional technical complexity. To use our model, we have to create the building model and to calibrate and to validate it. And so the calibration was performed manually using an iterative procedure in which parameters are adjusted until the simulation results aligned with the measured data. Validation occurs when this iterative process is finished. And when specific metrics are used to determine the level of real-world representation achieved by the model. The different acceptable values for these metrics are provided by different international guides, just written here. And once the building model was validated, we modified the different entries relating to the use of ceiling fan and windows in two ways. A case integrating the behavior models developed using the Python plugging method, so the proposed model coupling methodology, and a case typically found in design office type simulation that we note after BE, where the different assumptions are made from expert knowledge. So first, we consider the case of a design office simulation where expert knowledge is used to make assumptions. Here we have tried to make assumptions that are representative of the method most commonly used by the professional. For example, here we assume that the ceiling fans were used at maximum power during the day in summer. Less use in mild season and not used at all during the winter period between May and September for Réunion Island. For the windows, we assumed that users open them all year long during occupancy hours. And so this kind of traditional models are regular and deterministic scenarios manually defined. We then compared the results of the conventional building energy simulation with the results obtained after applying our coupling methodology. The conventional simulation noted the BE on this graphic is in orange. And the results for our coupling methodology integrate employing the random forest classification model is in green. And in blue are the data actually measured in on site. What can we see with this graphic? We can see that our proposed method more accurately captured the on-off cycles of the ceiling fan compared to the traditional simulation, which shows behavior in the form of regular steps. We have also calculated some scores obtained for the different simulations, and the scores obtained validate the visual analysis of the curves because the coupling methodology outperforms the traditional simulation. We have tested different way to calculate the score with different metrics. And here we can see for the simulation of ceiling fan that the average deviation is 63% better than the traditional model. To conclude, we can say that we have some limits of the present work. For example, we have only modeled natural ventilation, so the use of windows and the use of ceiling fan, but not the use of, for example, a building with air conditioning. And we still have to improve the different models constructed. But it's a topic that we are working on, and we have to extend field measurement studies to other building types and other users categories to better teach models, and also to implement the coupling between ceiling fans and air conditioning for other building, and to represent more kind of building. Thank you for your attention, and now I let the place for Mathilde from the CEREMA. We will speak about observing and modeling window states in French dwelling monitored during a summer with heat waves. Thank you.